So in this lecture, I want to use the sort of symbolic logic we've been learning, very briefly, but, just the basics. I want to use it to start thinking about inductive logic or inductive reasoning. So far, just the very basic stuff we've been doing is symbolic logic with regard to deductive logic. And, deductive reasoning is all or nothing. An argument's valid or it's not. And in deductive reasoning, you either treat a statement as true or false. It's all or nothing. And, honestly, as I said before, you can replace these true and false with numbers, right? True with 1, false with 0, right? Again, as I also said, this is a lot of the way that computers think, right? True 1, false 0. Deductive logic, this sort of symbolic logic is key to the very idea of making computers, right? So look, you could treat, A equals T equals 1. Well, if A is true, then not A is false equals 0, right? So on and so forth. If A is true, A or B has to be true, you get a 1 for that, right? A and B, well, it all depends on whether B is true. If it's B and A are true, you get a 1. If not, you get a 0, right? So on and so forth with the trues and false. But remember, inductive reasoning isn't like that, right? Inductive reasoning isn't all or nothing. Inductive reasoning is all about probabilities, right? You don't say, well, is the argument valid? You say, is the argument strong or weak? And strong means there's much greater chance of the conclusion being true. Weak means there's a lower chance of the conclusion being true. Well, how do you use inductive reasoning? So how do you use symbolic logic, these symbols we've been learning, with inductive reasoning? So the first thing you do, the most basic thing, is just to put a PR in front of the letters, right? PR stands for probability that. So probability that A means the probability that A is true. Probability that B means the probability that B is true. And you can put more complex formulas in using symbols, right? Probability parentheses not A, probability parentheses A and B, probability parentheses A or B, right? You can even do more complicated, right? Probability not A and B or C. All right. Well, how do you model this idea, that there's, we're not dealing with certainties, we're dealing with chances, right? With your statements in deductive logic, you have true equals 1, false equals 0. With probability of A, you can assign numbers between 1 and 0, representing the percentage chance or the fraction, the odds that it's true, right? So probability 0.5 or probability that A of 0.5 or 1/2 means that we think there's a 50% chance that A is true. Plug in whatever you like between 1 and 0, right? Can't go above 1, can't go below 0, right? Think of this in terms of percentages, right? 101% makes no sense. Negative 1% doesn't make any sense either, right? There was a stupid deodorant commercial back when I was a kid that was like, when you need to give 110%, right? You can't give 110% no matter what, some dumb ad man thinks, right? You can only give 100%, right? So, chances between 0 and 1, usually some fraction, right? Well, look. Even if we have a number for probability that A or probability that B, how do we figure out probability that not A? Probability that A and B, probability that A or B. Much less something more complicated like probability that A or B and not C, right? How do you figure this out? Like, you can't use a truth table, right? Truth tables, again, are this all or nothing reasoning. They don't give us any formula for working with fractions or working with percentages. Well, let's start with an easy one. Let's start with the probability that not A, right? So if I tell you the probability that A is 1/2 or 50%, then what's the probability that not A? Let me give you an example. If I tell you there's a 50% chance the Braves win the World Series, then what's the chance they don't win the World Series? If I say, what's the chance the Braves win the World Series given there's a 50%, or sorry, what's the chance they don't win given there's a 50% chance they win? Say 50% chance they win, what's the chance they don't win? This is not a trick question, right? It would also be 50%. So this gives you a general formula, right? The probability of not A is 1, remember 1's our highest number, minus the probability that A, right? Or you could think of this in terms of percentages. You know, probability that not A equals 100% minus how, the probability that A, however many percentage we give it. And this works with any expression. This is, if I throw out something super complicated like this whole string of, complicated stuff here, the probability that A or B or C and not D or E, Lord, I don't even know what that would look like as a sentence. I just start typing letters. But we would know it equals the probability of 1 or 100% minus whatever fraction or whatever percentage, if we're using percent, of this probability that not A or B or C and not D or E. Okay. So I will say to you, this little formula, that the probability that not A, and you can, equals the probability equals 1 or 100% minus the probability that A, when you think about it, it's pretty obvious, right? What's the chance? Well, what are the chances that the Braves don't win? Well, it's 1 or 100% minus whatever the chances they do win is, right? But this is often super useful in solving problems. We'll see in the Weisberg book, there's some of these that look super complicated until you remember this and plug it in. So, what about probability A or B? What in the world will that be? If we know the probability that A and the probability that B, what in the world is the probability of A or B? Even more complicated, or sorry, not even more complicated, but, also maybe hard to figure out, what's the probability that A and B? How do we figure that out? Well, we'll talk about that next lecture, but in this lecture I want to end with just a very general question that I think will help us start to get into this. If you had to order it in order of probability, how would you rank probability that A versus probability that A and B and probability A or B? Some of y'all are saying, well, I have no idea. I have to know what the probability of A and B is, or at least B, you don't. You can actually come up with a pretty good ranking and a pretty good justification of these without knowing anything about A or B. What is it and why? Well, we're talking about inductive logic, but I think the truth table for deductive logic might give you a hint here. Ask yourself, is it easier for A to be true or A and B? And is it easier for A and B to be true or A or B, right? This disjunction. Think about that, and we'll start with these questions next lecture.